Hi, we're Team 21. Our project is a lower-level human-guided image classification model. Deep learning neural networks have been proved successful in image classification tasks. However, they can be vulnerable to adversarial attacks. They can misclassify inputs with only small but intentional wrong perturbations. The picture on the right is a famous example. There were many common practices to improve model robustness. For example, data augmentation, gradient regularization, randomization, etc. Recently, Gill et al. Proposed a new concept of human-guided approach. By human interacting with the machine learning system, we incorporate human knowledge into the model, and this will produce elevated performance than the original model. However, there were few discussions in this domain. So our team took on this challenge and explored human-guided learning's impacts in improving the robustness of image classification model. The first step is to find out the entry point that human intervenes with the model. Here is a diagram of a simple CNN model. As we may already know, the first part of CNN are feature extractors, and then followed by a final feature classifier. Our concept is to add an additional lower-level feature learning layer and use our specified SHIP dataset to train the layer to improve the model's robustness. But why this would work? First, one important aspect of CNN is to obtain abstract features. For example, the edge might be detected in the first layer, and then simpler shapes will be detected in the following layers. By manually adding a layer after the lower level output and an additional loss function on it, we can put human guidance in the layer by specifying the shape it's gonna detect. Here comes our deep learning model pipeline. There were 4 stages: data collecting and pre-processing, baseline model training using CIFAR-10, human-guided learning with additional SHIP dataset, and lastly, evaluating the robustness of 2 models. Let's dig into the data. For the baseline model, we select CIFAR-10 dataset, which contains 60,000 images with 10 classes. And the data we use to train the lower level layer is called 4Shapes from Kaggle. It contains 16,000 images of 4 classes: square, star, circle, and triangle. We choose ResNet 50 as our baseline. Since this project has not been done previously, we use a model that we have prior experience with. In addition, ResNet also has pretty good accuracy in image classification tasks. Here is our modified structure of ResNet 50. We add a linear layer and a loss function before the first bottleneck. The 4-ship data will go into this layer and update the loss here. The CIFAR-10 dataset will go to the rest of the ResNet layer and update the output loss. We add the 2 weighted loss together as our final loss. After training, both models achieved an accuracy of around 94%. To evaluate whether the robustness of the human-guided model improved, we evaluate them by using 2 adversarial attack methods on the input data: the fast gradient sign method and Collinen-Wagner method. Here is the result of the baseline. Using FGSM and controlling the epsilon, which is perturbance level, the accuracy drops quickly from 0.95 to 0.3. Using CW method, the accuracy drops to 0.1. Our human-guided model defends the attack better by achieving a higher accuracy for all epsilon values using FGSM method. It does not show significant improvement using CW method. This table shows a side-by-side comparison between the human-guided model with the baseline. The human-guided model shows a significant improvement on the accuracy with all epsilon values using the FGSM attack. The improvement maximizes at epsilon value of 0.06, which is around 21% increment. Lastly, conclusions. Our method shows that human-guided lower-level learning could really help in improving robustness on FGSM adversarial attacks. The improvement is significant enough, and the new method only requires some simple SHIP dataset and costs little more training time. Looking forward, we could extend our work in many ways. For example, we may teacher force more low-level layers instead of one single layer. That's all. Thank you for watching.